Greetings, everyone. Today we're going to be looking at gravitational forces in 2 dimensions, not just one. This means that we'll be looking at multiple objects in different orientations, all exerting gravity on a single object. This is going to be a very important skill for next semester when you have, for instance, one test charge and multiple other charges acting on that charge. It's very, very common in electrostatics to have questions just like what we're going to see today, but with gravitation instead. How do we deal with gravitational forces in 2 dimensions? Well, there's a procedure that we can generally do. First, let's remember our equation for the force of gravity on an object. It's G, Newton's gravitational constant, times the mass of one object times the mass of the other object. Remember, you always have to have at least 2 objects to have a gravitational force, divided by the distance between their centers squared. The direction of this gravitational force is towards whatever is gravitating. So you always have one object that you're looking at that is being attracted, and another object that's attracting that object. And the force of gravity is towards the object that is gravitating. So this is the object that we're looking at, or the test object, and that's the object that has the gravity. You can always flip it and say, okay, now I'm going to look at this one, and that's going to be what is attracting this over here. And that's only going to flip those 2, but it will also flip the direction of the gravity towards the gravitating thing. Always good to keep in mind which object we're looking at and which object has the gravity. Now, if we only have 2 objects, and one of them is a test object that we're computing the gravitational force on that object, then finding the magnitude and direction of gravity is actually really easy. Well, it's just going to be towards that object. So you just figure out what this theta is. You probably even have to be told what that theta is. And you just plug in all the numbers in there, and you have the magnitude and direction of the gravitational force on that object from that object. That's kind of boring. So today we're going to learn how to deal with this for multiple objects. If there's a third object in here that's also attracting this object, what do we do in that case? First, we find the magnitude of the gravitational force from each object on our test object. That's our test object. If we can find the magnitude of the gravitational force of this object on our test object and of this object on our test object, then we've got step 1. We use this equation again to do that. Plug in the Newton's gravitational constant times the mass of the object times the mass of our test object. Remember, one of these is the mass of the gravitating object, the other one is the mass of the test object, the one that we're looking at the gravitational force on, divided by the distance between them squared. This should not be taken as m1 and m2 are that and that, for example, because that's the object that we're testing right there. Next, you want to break up each force. So we've got 2 gravitational forces, one on this object from that object, the other one on that object from that object. We need to break up each of those forces into their x and y components. Remember, all the way through the semester we've been doing that. So if you're not confident with that, then get confident with that. It's in the book, and it's probably in your calculus book, and it's online. Then you add up all the x components, and you add up all the y components. What do you get when you add up all the x components? You get the net force in the x direction. Adding up all the y components, you get the net force in the y direction. And then you can use the net force in x and the net force in y to find the magnitude and direction of the resultant force. Magnitude, how do we find the magnitude given the components? Yeah, Pythagorean theorem. How do we find the direction? Yeah, inverse tangent of the y thing over the x thing. Great. I have an odd star system that I want to look at. I've got 3 stars in this star system. This star here is going to be our test object, the object that we're going to be looking at the gravitational force on that. It has a mass of 10 to the 30th kilograms. It is 2 times 10 to the 12th meters from that star. Now these are all huge numbers. What do any of them mean? Well, our sun has a mass of about 2 times 10 to the 30th kilograms, so our test star is about half the mass of the sun. 2 times 10 to the 12 meters is 2 billion kilometers, which is somewhere out there between Saturn and Uranus, give or take. This star has a mass of 8 times 10 to the 30th kilograms. That's 4 times the mass of the sun. That's star 1, and star 1 is 2 times 10 to the 12th meters from star 2, which also has a mass of 8 times 10 to the 30th kilograms. We need to find the net force on star X, both X and Y components, and therefore the magnitude and direction of the net force. And we need to find the acceleration of that star, that test star. Well, how do we do this? Think back to our list of instructions. We need to find the magnitude of the gravitational force from each object on the test object. Okay, the magnitude of the gravitational force on the test object from star 1, which is this one, g times the mass 1 times the mass of star X, the test object, divided by the distance between 1 and X, the test star, squared. So we've got 6.67 times 10 to the negative 11, we've got 8 times 10 to the 30, we've got just 10 to the 30, and we've got divided by 2 times 10 to the 12th squared. That gets us 1.334 times 10 to the 26 newtons. And we've got that for star 1. Okay, star 2. Pretty much the same thing. The force from star 2 on the test star, g m2, mass of that one, divided by the distance between them squared. Well, what is the distance between that and that? How do we figure that out? Yeah, this is a triangle, and we can do Pythagorean theorem on that. We've got this side squared plus this side squared, take the square root, and that gets you the hypotenuse. Plug that in there, square it, and you get 6.67 times 10 to the 25 newtons. Does this make sense? These two stars have the same mass, but the force of gravity that they exert on this is different. Does that make sense? Well, this one is farther away. It's farther away, in fact, by the square root of 2. And so if it's farther away by the square root of 2, that gets squared. So you're ending up dividing by twice as much. And you see that this is actually exactly half of that. So that actually works out. Okay, what direction do you think that the net force is going to be given all this? I want you to think for a little bit about what direction you think the net force is going to be on the test star. Is it going to be this way? Is it going to be this way? Is it going to be this way? Is it going to be somewhere in between? Is it going to be exactly halfway between? Is it going to be a little bit above halfway between? A little bit below halfway between? I want you to think about that now that we've gotten these numbers. All right, make a hypothesis. We'll examine your hypothesis when we're done with this. we need to next break up each force into x and y components. We've got the force of star 1 in the x direction is, actually, why is it the same? Why are those two the same? Well, it's because that star lies exactly on the x-axis. So all the force is going to be pulling that way. Okay, what is the force in the y direction for star 1? Yeah, 0 newtons. What about for star 2? How do we get this? Well, this is the net force from star 2. And we need to break that force up into x and y components. Well, to do that, we need this angle. What is that angle? Yeah, that's 45 degrees. You can tell just by the two sides of the triangle being the same. So what do we do to this to get the force in the x direction? Now we have to multiply by the cosine of theta, which is 45 degrees. So this times the cosine of theta will get us the right value for x. And then for y, we multiply by the sine of 45, the sine of theta. And those are the same numbers, of course. What do we do with this? Well, we need to find we have found the x and y components for each of the stars. So next, we can find out the net force in x and the net force in y. That's step 3. Add up x, add up y. In x, well, we just add. We get that. In y, we just add. Well, 0 plus that is just going to be that. Great. Okay. And then we can find the magnitude and direction from those components. We find the magnitude by taking that squared plus that squared, taking the square root. We find the direction by taking the y component divided by the x component and taking the inverse tangent of that. Now, what was your guess on what the angle is going to be? Is it 14-ish, 15-ish degrees? Well, if it is, that's great. This is 45 degrees. That's 0 degrees. We're a little bit less than halfway between those. Halfway would be 22.5 degrees. We're at 15-ish degrees. We're at a little bit less than halfway. That makes sense because this is stronger than that. The gravity from this is stronger than the gravity from that because 1 is closer than 2. Therefore, 1 will be pulling a little bit harder than 2. If they had the same gravitational force on that point, then the angle should be directly in between them. But because 1 is closer, its gravity is stronger, and so the angle will be a little bit less than half. And then, finding the net force, well, that squared plus that squared square root gets you 1.866 times 10 to the 26 newtons. There. Now you can see the exponents over there. My apologies. And we can find the acceleration. How do we find the acceleration from this? Yeah, F equals ma. We've got the mass of the thing that would be accelerating. We've got the net force. We can find the acceleration from that pretty quickly. That's a pretty slow acceleration. Less than 1/1000th of a meters per second squared. So it's not going to be accelerating very much. And there's the number, yes. 0.000187 meters per second squared. I'm going to make a change to our weird star system so that we can see all this again. I'm going to take star 1 here, and instead of having it 2 times 10 to the 12 meters this way, I'm going to have it 2 times 10 to the 12 meters this way. I'm going to relocate it to be on the exact opposite side of our test star. And so that gets us this over here. I have taken star 1, which used to be there. I've picked it up and I've put it down over there on the opposite side. So now star 1 is there, star 2 is there. We need to do the same thing. We need to find the net force on star x, our test star, and find the acceleration of our test star. I want you to think, what is going to change from this? When we have our new setup, where we've just moved our star from there to there, what here is going to change? I'll give you a moment to think about that. Okay. What do we think? What's going to change? Well, let's look. This page is virtually identical to the previous page. We have just moved things over. We get the same force from star 1. We get the same force from star 2. Great. Okay. Well, what about the force in the x direction? There's no change to the force in the y direction of object 1, but because we have switched the location of object 1, of star 1, from being in the positive side to being the negative side, now this is going to get attracted that way. And so we get a negative sign right there. Positive sign there because it was in the positive direction. Negative sign here because it's in the negative direction that way. Other than that, there's no more changes. That's the one thing that changes. It does have follow-on changes after that. We've got a new force in the x direction there. Instead of it being a positive number, just adding those two up and getting that, you have to take them and this plus this, but it's a negative number. And then we can use our normal way of finding the angle and the net force. That squared plus that squared square root gets us that. When we do our normal way of finding the angle, though, we get negative 28.68 degrees, which would imply the force is in that direction. Is that reasonable? Should we be getting a force in that direction? One thing you can always do whenever you have a problem like this is try to judge yourself what direction everything will be in. Does it make sense for the gravity to be pointing that way on that star? Not really, no. Your calculator will say that's true, though, but that does not make it true. You know that it should be probably somewhere the other way. We're going to get a force like that and a force like that, and they're going to partially cancel out with each other and give us a resultant force kind of that way. And so we know that this negative 28 can't be true. Remember what we do with inverse tangents. Sometimes we have to add 180 when it's in the wrong quadrant. So add 180 to that, and you get 151.3 degrees. The net force is 9.83 times 10 to the 25 newtons. Actually, without looking back to your previous paper, do you know, can you hypothesize which net force is greater? Weird star system number 2? Is that force greater? Or is the net force in weird star system 1 greater when that star is over there? Well, when that star was over there, you kind of had the forces adding up. They're on the same side, so they added up a little bit. So you should have a greater force in star system 1 than 2. This is star system 1. We have 1.866 times 10 to the 26 newtons. Here we have 9.83 times 10 to the 25 newtons. So this is less. Weird star system 2 is less, just as we would hypothesize, also giving us a smaller acceleration right there.